my work we're already doing, and this work is in collaboration with my colleague, Zekeri, and my supervisor is Martin Humula, and we are in consultation with Jan Jutka. And so we are leveraging ontology-based knowledge representation for explainable malware detection. So the highlights of the presentation will be malware, we're going through malware, introduction of malware, ontology, explainability, then I'll present the motivation for the study, and then where we are presently and where we will be in the future. So malware it's short for malicious software, and it refers to any software that intentionally designed to disrupt or damage or gain unauthorized access to the computer system. And their common goal is to steal or cause damage to systems. And they are classified, or types of malware could include worms, rootkit, virus, spyware, ransomware. Like I will say, the classification of malware type most times depends on the author's view or perspective. According to the AV test report, malware-based software repository, in the last 12 months, they have registered, only in the last 12 months, they have registered over 1 million malware samples and portable unwanted files. The last 12 months actually is from January to December 2024. That is what it means. And then their record also shows that in every month, they record over 8 million malware, and every day they record over 288,000 malware. So the need to mitigate malware attacks cannot be emphasized as it continues to threaten the cyberspace today. However, all of this malware, we realize that according to their report, so far, as at January 2025, they have recorded in total over 1.5 billion registered malware. And of the 1.5 billion registered malware, about 800 and something million, over 800 million are Windows malware. And then in 2024 alone, they have registered about 1 million malware. And then 83 million of this Windows malware are Windows malware. Sorry, in general, they have about 1.5 billion malware. Over 8 billion of them are Windows malware. Then in 2024, they have recorded 1 million malware, and 83 million of them are Windows malware. And consequently, about 10 million samples registered only in January 2025, about 8 million of these samples are Windows malware. So all I'm trying to present here is the need to actually focus on Windows malware detection. If you can see the statistics here, over 80% of these are Windows malware. So that is why we're actually focusing on this Windows malware, because it's been attacked, it's the most attacked recently. All right, and so before we can actually build an effective malware detection system, there must be a need to analyze malware. So understanding malware behavior and harnessing the right features is a game changer for high-performance malware detection system. So to be able to build a malware detection system, you must actually have to understand what they do. Like I will say in my example, in your neighbor, probably there is an attack, armed robbery, any form of attack, and you have weapons within your possession. The weapons you have are not enough for you to actually mitigate that attack. You must first of all understand the nature of attack. Who are these attackers? What kind of attack? Is it an airstrike? Is it what kind of attack? If you don't understand and you go into the premises, the scene of the attack to mitigate the attack, you might be a victim of the attack. So in the cybersecurity world, understanding this malware, what they do, and the nature of the attack will help us to mitigate them. And so that is why we go into the study of malware analysis. That's what malware analysis is all about. And so this malware analysis, we have two types of them. We have the static analysis and we have the dynamic analysis. And so like in static analysis, it's trying to understand what the malware do or what the malware is all about without running them. Like When you look at, take examples from our culinaries, you look at kapustnica, for example, look at all the ingredients of kapustnica, look at everything about kapustnica, and you say, oh, I have known kapustnica. I know kapustnica by the time I see it, by the time I know the ingredient, by the time I see what is used to cook it. But that is what you do in static analysis, by analyzing it by your side. But what happens when the kapustnica is being prepared and cooked? Will you still identify the kapustnica anymore? So at this time it's been cooked, at this time it's been processed, it's been on fire, and it's been through a lot. But then what dynamic analysis does here is to monitor kapustnica on fire, see how it's being cooked, see how it's being boiled, and then you see how it behaves on fire, and then you also test it. So in that way, when you see kapustnica, when it's prepared, you will know this is kapustnica, and not just by the knowledge you have when it is raw. Is that okay? But also, when you depend on only the process of running kapustnica to understand what kapustnica is, without seeing it previously before it's being cooked, when you see the raw elements of kapustnica, you will not be able to identify kapustnica. So in either way, when you depend on one of these, something will be lost. I'm talking about there's limitation in static analysis, and there's as well limitation in dynamic analysis. So bridging the gap is what we call the hybrid analysis. You understand what kapustnica is in the raw state, and you have processed it and you know what it is. So in either way, in either form you see it, you will know that this is kapustnica, because you have harnessed the feature when it's raw, you also harness the feature when it is cooked. I know? So in general, the goal of malware analysis is to examine the code for malicious intent and to extract high features, the right features, in order to build a robust malware detection system to mitigate the threat posed by malicious software. Kuchimi kaputnicu, very dobre. All right, now we'll talk about malware detection. Malware detection is actually a set of defensive technologies required to identify, block, prevent the harmful effects of malware on host systems, and distinguishing whether a particular program is harmful or not. That is what it means. And before this detection, before you can build a detection system, there must be an analysis. That is what I actually said earlier. All right, remember that our goal is to derive explanation. So we are applying explainable model for detection, not just the black box that has been in existence. And then this is what explainable AI does. This is what the explainable malware detection is all about. In the black box model, when a detection is made, a black box model actually leaves us with the question of, you don't know why the machine makes the decision they made. Why did you do this? Why not something else? Why did you succeed? Why did you classify this as malware? What made you think that this is malware? The black box have no technique to actually give us this detailed explanation. But in explainable model, we can now, when the process is done, you can see that, oh, I understand why this is. I understand why not, and I understand when it succeeds. And I know when it failed, and I know why it doesn't succeed. So that is what the explainability does to us. And without explainability, it is challenging to trust the performance of this system to identify and correct errors in detection, analyze emerging or zero-day threat, and ensure fairness. So without this explainability, it will be very difficult to know why machines make their decisions. And when that happens, it will be difficult to trust the decision of machines. And so that is why we'll delve into explainability to know why machines are taking their decision. And then we can trust their result in totality. However, in a bid to delve into explainability for malware detection, research has shown that leveraging ontology holds potential for explainability for malware detection model. And that is why in this study, we are focusing on ontology-based model representation for malware detection. And what is this ontology? My colleague Zachary has made a lot of justice. His research is based on the ontology, and he has made a lot of justice to ontology. And I will not be talking about the mathematical whatever behind it. We are applying it to to malware domain. So it's a formal representation of set of concepts and their relationships in a particular domain. So now, in this malware domain now, it's called malware ontology. So it objectively describes things in real world. So it is often used to describe the knowledge of a domain. So leveraging ontology offers a consistent way to represent and describe malware actions, behavior, interaction between objects, which has the potential of enhancing detection and explainability. That is the clear and human interpretations. So in this research, what are we looking at? Malware dataset. Can we have a malware dataset with static dynamic features? Because like what I said earlier, the static features have their limitation, dynamic features have their limitation, and we are looking at bridging those things. So and no such dataset exists at the moment that is structured. So we're looking at, can we have a dataset with this set of features that we are looking at? And then if we have those datasets, can we have a structured ontology representation for malware feature integration? And also, can we have a knowledge-based malware dataset that is structured dataset now that is not the usual unstructured dataset? And then our explanation going to be any good at the end of the day? So looking at the previous efforts by researchers on ontology, on leveraging ontology for malware detection, then in 2009, applied ontology technique to malware domain and proposed a method for constructing malware knowledge base about malware individuals and families. His focus was just on malware individuals and families and not on malware detections. And however, the feature he actually used, he was based on dynamic features. He built dynamic features only, and it's based on malware families and not generally for malware detection. And then in 2022, Cowdrey also developed ontology for dynamic analysis using commonly observed suspicious behavior. The ontology was not designed based on standard language. Yeah, he designed the ontology quite okay. Even though it was limited to family classification, no language was used. And as we continue, we will see the importance of using language, of applying a particular structured language in building our ontology. Then the closest to our work is the P-malware ontology by Schwartz et al. In 2024, which offers a reusable semantic schema for portable executable files. While this ontology used the MIC standard for characterizing malware feature, it only integrates features from static malware analysis, which definitely will possess the feature of the limitation of static analysis. And we are trying to also bridge this gap by harnessing the potentials of dynamic analysis and then have a hybrid features for our ontology. So while leveraging ontology also holds the potential of enhancing explainability, most efforts in literatures are focused on static malware ontology, covering limited features in expressing the actual intent or do not adhere to any standard language for characterizing malware attributes. Hence, there's a need for a more complex ontology to handle the continuous fast-rising impact of malware into this world. So this is what we'll be doing. So such ontology is currently not in existence. And we will be building an ontology. We'll be proposing an ontology with vocabulary formalization that is based on an established standard language for feature representation. Specifically, we are combining the MIC, the STIS, and the MITRE standard for ontology. And this is the workflow this is the general research workflow. And like for basic objectives, we're defining our classes, and then designing our ontology using Proctogy, and then we'll arrive at our ontology knowledge representation. And then here we'll have to be running the malware analysis by getting raw malware samples, run the analysis using analysis environments, then have a hybrid analysis, and then extract features. At this point, we'll have a data set, but they are going to be unstructured. And so what will bring us to a structured data set is by the time we combine this feature, integrate these extracted features into the ontology that we have now designed, then we'll arrive at this structured data set. And then from here, at this point, we can apply explainable model to find out if we can actually have a better explanation from what already exists. So this is where we are, the malware ontology. So like I said earlier, we can describe malware ontology as knowledge model for malware domain. And it contains all the relevant concepts related to malware, behaviors, malware classes, and individuals, and the computer system components. So this is the way it looks generally. The malware ontology, we have the malware and we have the system component. So to achieve its purpose, malware needs to act on a system component, such as deleting files, hiding process, changing registry, and then there should be a system component classes which consist of the target malware will act upon. And then there is a predicate which describes the relationship between the subject and the predicate and the object property is used to represent this relationship. So we have malware which acts on system components. And in our representation, in our formalization, classes are named with capital letter, first title case, and then properties are named in this way, starting with small letter, and then when there are two names together, it has a capital in between them. And the system components are also named this way. It also helps us for collaboration, and it's for formalization. And then we also use the MIC vocabularies in building this ontology. To build a standard malware characterization for a malware ontology, we use the malware attribute enumeration and characteristic called MIC, a formal language for describing malware information. It's a formal language for describing malware information. And the reason we are using it is because it's widely acceptable by the community. And it's one of the best formalizations so far. And the MIC standard is reinforced by structured threat information expression, which is TIS, to define several top-level objects, that's TIS over observable objects. All right. Looking at the MIC vocabulary, it consists of the MIC objects with behaviors, collections, and then the MIC objects generally, like the malware side of the ontology, and then it also consists of the observable objects. Like I said earlier, malware needs to act on system components. The observable object consists of the system components that the malware will act on, and then a relationship that also defines the relationship between this malware and the system component and how they relate generally. And so we have the malware, and then when the malware analysis is carried out, there is features, the feature set, the static features, the dynamic features, and the analysis method, they are now integrated into these vocabularies. So the MIC standard is a good choice for our characterization because it integrates the STIS and matrix vocabularies, which captures and represents more malware attributes. Also, the MIC is supported by major analysis tools like Cuckoo and integrated analysis, and in integrating analysis results. Also, we use Protege for this ontology. In building the ontology, while we use the MIC vocabulary, we use Protege to build the ontology. And a number of software, of course, a number of software tools are available, but in this study we are using the Protege, and it is the most popular software with easy to use interface and for building and maintaining ontology. Protege supports web ontology language, which includes plugins for reasoning and visualization. That is one of the reasons why we're also using it. Ontology language. A formal language used for describing and structuring data in the semantic web. And one of the languages of ontology that is commonly used is the web ontology language. Web ontology language is one of the languages, commonly used language for ontology, in building ontology. In this study, we use the web ontology language, which is one of the commonly advanced ontology languages for knowledge representation, equipped with semantics such as classes, relationship, restriction, and reasoning. It's used for complex, the ontology language is possible, it can actually integrate complex knowledge representation. And the knowledge we are trying to represent here is quite a complex one, and we have to make use of the web ontology language. It is a more expressive, it's also very expressive language for designing complex ontology. We support the extension of RDF and with richer semantics such as the property restriction, equivalence, disjointness, and enhances reasoning and inference. This is the UML, this is the model of our ontology. So before we're able to build the ontology, we model them. We have a model of it using, and this model is informed by the MIC vocabulary. So we have to follow the MIC vocabulary to make this model. This is just a section of the model. If you look at it, you can see the observable object. Like I mentioned earlier, in the MIC vocabulary, we have the MIC object and we have the observable object. And this is the observable object, and this is a MIC object. This is the MIC object. Malware action. Of course, malware action, and this is the relationship between them. Malware action has input, observable object, which in the representation, we said, in the ontology, we said, malware action is the domain of this object property input, while observable object is the range. Also, malware instance has instance observable object. So has instance is the object property, and the domain of this is the malware instance, while the range is observable object. So this model has actually shown the MIC object, observable object, and the relationship between them. And so this is the visualization of the malware ontology after it has been modeled in Protege. And so this is just a collection. Collection is MIC object, and it also has a subclass called process entity. So process entity is a subclass of collection and all. This is just one of the classes. And also, this is observable object. Observable object has a subclass activate, has a subclass file. File as well has a subclass archive file and all. Even software also, if you look at software here, okay, software has software is a subclass of observable object. If I allow this to expand further, you will realize that software also has a subclass called operating system. And if I open the operating system further, you will realize that operating system also has subclasses as Windows operating system, Linux operating system, and all the operating system we are using. And when you open them further, you will realize that those operating systems have their virus individuals, like in form of the version of the operating system they have. And that's one of the things about the ontology we are building is that it's extendable, and it does not just depend, it will not just be used for Windows malware representation. It can be extended to any of the Windows, unlike the previous ontology that exists that are quite limited. But if any other researcher picks up this ontology in the future, he could extend it to and tailor it to what he wants to use it for. And then one of the advantages of the standard we are using in MIC is by the time you use a standard vocabulary, a researcher picks it in the future and he wants to extend it, he has a document to make reference to. Like, okay, this is the language used, this is the format used. If he will extend it or do anything to it, he will do it based on the language, based on the formalization of that language. Unlike the existing ontology that if we want, before we arrive there, we examine previous and various ontology to see if we can extend it to use it for what we can do. But when we laid our hands on them, we couldn't find the language or the formalization that was used or that is used to design the ontology. It makes it not to be useful for us to extend our feature. So the work we are doing so far will actually encourage further research progress in line in this direction of ontology. All right. Further, you could see observable objects, and then you see that there is also such a thing as data property. We talk about object property tells us the relationship between classes, but data property actually tells us about the property of the particular class, of the particular object. And you could see that there is such a data property as candidate, and then it has a range as date stamp, like a data type, string, data timestamp, and all of them. Now, observable object also has a subclass called artifact, and the artifact has a data property called payload bin, and the payload bin has a data type called this binary, also string, URL, and the rest of them. So all of this data property helps the machine to have the detailed information about the object in concern or in question. Also, I can mention that in the mic vocabulary, there's mic object and there is observable object, which is similar to the system component. There is also relationship, which defines the relationship between those objects. We also have represented the relationship in our ontology. And the relationship has a subclass relates to, and for the subclass extracts from, has distance, and ancestor of. And also, this is just to show the relationship that I showed earlier in the model, in the UML model. Observable object. This is a malware action. Malware action has a relationship with observable object, where malware action is the domain and the observable object is the range. Output object, input object. Also, another mic object malware family has relationship with the subclass of observable object called artifacts. Common code. Common code, in this case, malware family is the domain, while artifact is the range. And malware family also has relationship with behavior, common behavior. And of course, literally, you could see this, even if you are not in cybersecurity, that malware of the same family, of course, have common behavior. That is the relationship that is being modeled and all along in the ontology. And all of this relationship also helps the machine to infer knowledge effectively. All right. By the end of the day, in our ontology, we're able to relate it with previous ontology. This ontology in 2022 by Code Huri may not be the best to compare ontology with, but they were able to present the metrics, their basic ontology metrics. So we're able to, let's compare with them. But the distance, of course, is very far. While they have an ASIANs of 557, we have 2,982. In general, our ontology ASIAN is 5 times bigger than what they have. Of course, it's not surprising because they are just based on dynamic features and just on family classification. However, ontology is based on dynamic features, static features, and malware detection and family classification. And it can be extended not just for Windows, but for Android and for Linux and Mac as well. So it's a very large and complex ontology altogether. And then the logical assumptions count, we are 6 times bigger. Class count, we are 18 times bigger. Object property, we are 13 times bigger. Data property, we are 35 times bigger. And individual property count, we are over 2 times bigger.
And bigger is better?
Bigger is better. Bigger means more informations are being computed, and then it will help the machine to infer better knowledge and better reasoning from the ontology. The bigger, the better. Thank you.
Just to your remark, because you didn't mention the speed, how the ontologies are used. And if you want to detect something on runtime, the speed is crucial factor. In that case, probably bigger is not better. Usually, you need something very fast to infer something very fast, and a very complex description could be slowing down. Is it true or not?
Yeah, you are correct. We're talking about maybe the trade-off between computational overhead and performance. But however, in this case, what we have just done is we have represented this knowledge. When we start to apply the explainable AI or explainable model, then we will put this into consideration. But however, the bigger knowledge we have represent here will not have anything to do with the model we will apply eventually. Yeah. So that is the result in general. So in the near future, so this is where we are right now. In the near future, which we already started after we have finished this ontology, is running the malware analysis. Because this is we have just represented the knowledge. And then when we have run the malware analysis, we will extract malware features. And by the time we have extracted this malware feature, is what many researchers could have as the data set that they have been using for malware experiment, for malware detection. We will now have what we call the unstructured data set, which does not encourage explainability. Okay, you cannot derive explainability from unstructured data set. Or even better still, if you make an attempt, you will not get any good results from it. So at this time, we will get into this in the near future. Any moment from now, we are already on it here. We will arrive at the feature set for this. And then when we are done with that, in the future, we will integrate the data set or the features that we have obtained from the hybrid analysis. We will integrate it into the ontology. Because at this point, the ontology is just empty, it's just a knowledge representation. And then when we are able to integrate those features into the ontology, we now arrive at what we call the structured data set. And from this data set, we can now use it to you can now apply explainable model on it, and you can get interpretations, very good interpretation. Because like I said earlier, researches show that ontology enhances explainability. And that's why we are going through all of this route. And so in the far future, having achieved all of this, we will now going to validate the data set through application of explainable model to see if our explanations are going to be any good from what like the Schreck et al. Has. And then my colleague Anthony also used in his experiments for explainable malware detection, but the data set is based on structured static features. The data set is just based on static features. And then we will test our data set to see if we have a better explanation than he will do. So what we intend to do is to actually, first of all, use one of the model exactly that was used for that data set. Using the learn model to test it on this data set in particular, to see if we are going to have a different or a better and improved explanation from what they already have. And then we can say, oh, of course, we have a better explanation. And then subsequently, we can now begin to apply novel XAI model for improved explanation. So, dziękuję wam za pozorność.